So the next video that we're going to make sort of draws from what we just talked about in the previous one. So when we talk about integration and we talk about the rectangles, we jump back there just for a second. What we're noticing is that we're getting an approximation, but sometimes it's not very good. So this guy, if you look at our left endpoint, we were missing a bunch of area, so it was really low, 1.75. And this one was too big. We missed under the curve and sort of overshot it. So we have extra area. This one's not bad. It's pretty close. The answer, the actual value of the integral is 2.6 repeating, so it's pretty close, but it's not perfect. So what we want to do is we want to kind of extend our thinking of putting rectangles in there and think what would happen if we drew an infinite number of them. So what would happen if I drew an infinite number of rectangles underneath a curve? What would happen is that each of the rectangles would then be infinitely small, right? They would be infinitely thin. And because of that, they would actually be at every particular x value. There'd be an infinite number of rectangles and there's an infinite number of values. So each value would have its own rectangle. So what happens is the base of each rectangle gets denoted by this dx. And the height of each rectangle would be the function at that x value, whatever x value it happened to be. So the area of each rectangle would just be f of x times dx, base times height. And all we want to do is take the sum of those. And so we infinitely sum them, and we use that symbol right there. That is called an integral. Very exciting stuff. These are our limits on the integration. Sometimes those are there, and sometimes they are not. If they are there, it's called a definite integral, okay, because it has a defined value. If there are no restrictions, it's called an indefinite integral. So the distinction is that definite integrals have limits on the integration. That's the lower limit. And this is the upper limit. If those aren't there, then we consider it to be an indefinite integral. If they are there, then it's considered to be a definite integral. The definite integral gives you a value, a number. It gives you a constant of some sort. It gives you 2.6 repeating, for example, that we just saw. The indefinite integral gives you an actual function. So it's very similar to the derivative giving you the slope of the tangent. That was a constant. It was a number. Versus giving you the derivative function. So the indefinite integral is it's the sort of family of curves or the expression that is algebraic in nature that gives you the area if you plug x's into it. All right, so it's very similar to the derivative of x squared being 2x, but the slope of the tangent of x squared at a particular point, let's say 5, is 10. It's very similar. Another way to look at integrals is not just to think of them as an infinite series of rectangles. It's also to kind of consider the derivative of the area function. So imagine with me, and there's a lot of stuff in here, so let me just get rid of some of it for now. Imagine that that area underneath of my curve is actually a function. Okay, it's a of x. So I'm going to just color that in again. This is the area we're talking about. We say that's some area, but it's a function of x. All right, and let's say I want to take the derivative of that area function. So imagine that I want to take the derivative. Now the limit definition of the derivative, you remember, hopefully, is this. All right, except we're used to it being f, but our function now is a. So we get this. We say that's the derivative. Okay, and hopefully you're with me so far. Then the numerator of this function, this part, is the difference of two areas. It's the area between a and x plus h, and the area between a and x. Okay, so what do we mean? Well, imagine that if I go back up here, I'm just going to erase this part so you can kind of imagine what we're doing. A starts the interval, x ends the interval, right? That's a of x. So imagine that we're sort of saying a of x plus h would be, if I add h, assume this is h, would be this other area included, right? That's what we're saying. So imagine that sort of continues, and that we have, that's a of x plus h. And what we're going to do is we're going to say, let's imagine that c is the midpoint between x and x plus h. All right? So imagine that we put c, if that's h right there, I'll move the h over because it looks like h is in the middle instead of at the end. Imagine that I put a, let's call that c. I put a rectangle right here whose midpoint is at c and whose base is x plus h, right? If you can imagine that. So I'm saying I can approximate the difference in the area by that. All right? So if we let c be the midpoint between x and x plus h, then this difference of areas can be approximated, and we're only getting an approximation by the area of the rectangle f of c times h. So we're taking this, and we're saying that's going to be approximated by the rectangle that is f of c times h. The base is h, because we're starting at x plus h, and we're subtracting x, basically, so we have h left. And we're going to end up with just f of c. All right, so as h approaches 0, then this approximation gets smaller, because as h goes to 0, then the difference here goes to 0, which means this is going to go to 0. That rectangle is going to get progressively smaller. Okay? And so what we're saying is, as this approaches 0, this is going to get smaller. But as the h gets smaller, what happens is, because c is in between x and h, so imagine c is right here at the midpoint, and as x approaches h, so h is now here, then c is right here. And then let's imagine that h gets even closer, then c is in the middle of that. And so what we're saying is, as h approaches 0, c, the midpoint between x and h, is actually going to approach x. And so what we can say is that a prime of x is equal to, and just to see how I jump there, the limit as h approaches 0 of f of x. But f of x, because there's no h in it, is not affected by the value of h going to 0. So this just basically drops, and I get that. All right? And so what that proves, what that shows us, is that the area function, when you take the derivative of it, gives you the function f of x. And so what we're trying to do essentially is do the opposite. We're trying to do the antiderivative. Okay? And it's not important really that you understand all of the proof of that, but it is important that you understand the concept behind it. So if you look at the example that I wrote down here, if I have a function that's x squared, then the area function is going to be x cubed over 3 plus c. And the reason that it is that is because if I take the derivative of this, the derivative of x cubed is 3x squared, right? So if I find a prime, I get 3x squared divided by 3, and then the derivative of a constant is 0. The 3's cancel, and I get x squared back. So I'm essentially trying to take the antiderivative, okay? And you might be wondering, where did that plus c come from? What is that all about? Well, that's there for every indefinite integral, and it's there because the derivative of a constant is 0, which means when I integrate or take the antiderivative, it's always possible that at the end of the x squared, there's a plus 0 that we just didn't put in, and that becomes a c when we take the integral of it. So every single time you do an indefinite integral, you always need to put a plus c on the end. Okay? But the nice thing about this concept is that if you know derivative rules and you know the derivative of things, then you can kind of reason backwards to find the antiderivative or find the integral. So imagine I gave you a question that was like this. And let me just cover it up here. So you've probably seen it at this point, but let's say I said I want the integral. This is the antiderivative. All right, so that's what they were saying. It's the antiderivative, the integral of x plus 3. So I have to think about what derivative, the derivative of what is x. Okay, so we know the derivative of x squared. The derivative of that, if you take the f prime of x, if this is f of x, okay, f prime of x would be 2x. So we know the derivative of x squared is 2x, which means the derivative of x squared divided by 2 should give me x. Okay, so you can kind of reason backwards. That's essentially what we're doing. And with 3, we know that if we want the 3 to stay, then we need a 3x. And then we always put a plus c. So conceptually, what we're doing is we're kind of thinking, how do I take the function that I have and figure out the function that derivative is the function that I have. So I need to think about if I take this, all right, my result, and I take the derivative of it, I should get back to here. Okay, now you might be wondering, well, I'm not getting that. What are you talking about? Or, well, that's great, but I don't get the reasoning behind it. Well, the nice thing is there's actually rules for derivatives, and so there are rules for integrals because integrals are antiderivatives. And so we're going to talk about those, and we'll talk about those in the next video.